Hey everyone, welcome to my channel. Today we're diving deep into a project that's been my passion for the past year, my DIY harmonic drive mount for astrophotography. Grab a coffee, get comfortable, and let's embark on this astronomical journey together. First off, why build a harmonic drive mount? Well, it's a combination of passion, curiosity, and, let's be honest, a bit of a challenge to my wallet. I've always been fascinated by the precision of harmonic drive mounts. I remember drooling over the RST-135 by Rainbow Astro years ago. But when I started seriously looking into building one about 2 years back, I hit a wall. The harmonic drivers alone cost around €400 each. For a student like me, that was way out of reach. But here's the thing about us astrophotography enthusiasts. We're a persistent bunch, right? Fast forward to August of this year. It's that magical time when we university students finally have a breather. Instead of binge-watching Netflix like a normal person, I found myself diving back into research on harmonic drives. And guess what? AliExpress came through. I found harmonic drivers at a fraction of the cost. It was like the universe was saying, "Okay kid, here's your chance." Now, let me walk you through the journey from that eureka moment to the final product. It all kicked off in September. Picture this, my desk covered in sketches, my computer running CAD software nonstop. I was knee-deep in calculations, trying to figure out the perfect reduction. After countless cups of coffee and probably a few gray hairs, I settled on a 100:1 ratio for both RA and DE sec axes. Let's dive into the nitty-gritty of harmonic drives for a moment. For those unfamiliar, a harmonic drive consists of three main components: a wave generator, a flex spline, and a circular spline. The wave generator is an elliptical piece that rotates inside the flex spline, causing it to engage with the circular spline at 2 points. This creates an incredibly precise gear reduction. In our case, for every 100 rotations of the input shaft, we get just 1 rotation of the output. This level of precision is crucial for tracking celestial objects across the night sky. Then came the design phase. Initially, I was all set on making a cylindrical design, inspired by the sleek look of the Sharpstar Mackay. But here's a pro tip. Sometimes, practicality trumps aesthetics. I switched to an octagonal design. Why? Well, try drilling precise holes in a curved surface without specialized equipment. Not fun. The octagon gave me flat surfaces to work with, making the whole construction process much more manageable. November rolled around, and with it came Black Friday. Now, I know what you're thinking. Black Friday is for buying gadgets you don't need, right? Well, not for this astronomy nerd. I snagged those harmonic drivers and all the electronics I needed. It felt like Christmas came early. Let's talk about the heart of the mount, the electronics. I based everything on the OnStep software. If you're not familiar with OnStep, it's this incredible open-source telescope controller system. It's like the Swiss Army knife of mount control. For the brain of the operation, I chose a Physit TE4. Why this board? Well, it's commonly used in 3D printers, which means it's robust, well-documented, and bonus point, affordable. Now, assembling the electronics was an adventure in itself. Picture this, me, surrounded by wires, stepper motors, and driver boards, feeling like some mad scientist. The key components? 2 NEMA 17 stepper motors, one for RA, one for December. These aren't your average stepper motors, mind you. I went for high torque versions to ensure smooth movement even under load. Connecting everything was like solving a puzzle, but with the potential for small explosions if you get it wrong. No pressure, right? But here's the beauty of it. Once you understand the basic principle, it's quite straightforward. Power goes in, signals go out to the motors, and a USB cable connects to your laptop for control. Simple in theory, slightly more nerve-wracking in practice. One of the biggest challenges I faced was tuning the stepper motor drivers. These little chips control how much current goes to the motors, which directly affects their performance. Too little current and the motors don't have enough torque. Too much, and they overheat. I spent days tweaking these settings, using an oscilloscope to monitor the current waveforms. It was a delicate balance between performance and reliability. Let's move on to the mechanical assembly. This is where things got hands-on. I started with 3D printed parts for prototyping. Pro tip: always prototype with 3D prints before moving to metal. It saves you a ton of headaches and materials. The main challenge was ensuring everything aligned perfectly. Even a millimeter off, and you can kiss smooth tracking goodbye. After several iterations, and I mean several, my 3D printer was working overtime. I finally had a design I was happy with. Then came the upgrade to aluminum. I used a local laser cutting service to get my parts cut from 10mm aluminum plates. The precision was incredible. We're talking tolerances of less than 0.1 millimeters. Assembling the final version was like putting together a high-stakes puzzle. Each harmonic driver had to be perfectly aligned with its stepper motor. One aspect I haven't mentioned yet is NEMA 17 reduction gear system. While the harmonic drives provide the main reduction, I added a stepper online reductor on each axis for additional reduction and to act as a clutch mechanism. Designing and implementing this system was a project in itself, but all that effort paid off when it came time for testing. I loaded up the mount with my imaging rig, an AISI 585 camera, a Samyang 135, and a small guide scope, which, by the way, is another DIY project I'll tell you about in a future video. The moment of truth came on a clear night last month. I started with short exposures, 30 seconds, then 60, then 90. The stars were pinpoints. The guiding error was consistently under 1 arcsecond. For a DIY mount, this was beyond my wildest expectations. Now, I know what many of you are itching to ask. What's the damage to the wallet? Well, the total cost came to about €650 or roughly $700. This includes everything except the tripod and equatorial wedge. Is it cheap? Not exactly, but considering commercial mounts with similar performance can run into thousands, I'd say it's a bargain. Let's break down the costs a bit more. Harmonic drivers, €300. Stepper motors, €100. Electronics, SKR board, power supply, etc., €50. Aluminum parts and machining, €170. Miscellaneous, bearings, screws, wires, etc., €30. Of course, this needs to account for the countless hours of work put into research, design, and assembly. But for me, that time was an investment in learning and personal growth. Looking ahead, I've got some ideas for future improvements. I'm considering adding encoders to both axes for closed-loop control. This would allow the mount to detect and correct any missed steps, potentially improving tracking even further. I'm also toying with the idea of 3D printing a lightweight carbon fiber reinforced housing to replace the aluminum one, which could significantly reduce the overall weight. Before I wrap up, I want to emphasize something important. This project isn't just about saving money or showing off DIY skills. It's about understanding the technology we use in our hobby at a deeper level. Every time I use this mount, I feel a connection to the stars that goes beyond just observing. I built the machine that's helping me explore the cosmos. How cool is that? For those of you inspired to try this yourself, I've got good news. Every single file, every component list, every bit of code, it's all available. Check the video description for links to my Maker World profile. I've made this project open source because I believe in the power of community. If you build one, improve on my design, or just have questions, let me know. As we wrap up, thank you all for sticking with me through this deep dive. Astrophotography is more than just a hobby. It's a constant learning and improvement journey. Whether you're shooting with a high-end commercial mount or a DIY creation, remember that we're all united by our love for the night sky. If you enjoyed this video and want to see more like it, you know the drill. Smash that like button, subscribe, and hit the notification bell. I've got more DIY astronomy projects in the pipeline, including a video